Okay, so we were talking about the following problem. We said that the only unknown is the current. So we wrote the energy balance and we solved for the value of the current. And now if you want to compare the importance of heat transfer by free convection and radiation exchange, all we have to do is the following. We have calculated the value of Q radiation, and we know the value of Q convection. And we know that the total loss is the summation of both. So the percentage of radiation relative to the total flux can give us the importance of heat transfer by radiation. So if you want to find percentage of radiative flux, all we have to do is to divide Q prime radiation. Now, what is the dominant mode of heat loss? Is it radiation or convection? So we divide by total Q lost, Q prime lost, which is divided into two parts. So it is equal to Q prime radiation plus Q prime convection. And then we'll have the following. We can see that convection represents 55% of the total heat transfer. So we can deduce then that radiation will be 45%. Okay, so here in this problem, the heat transfer by convection is larger than the one transferred by radiation. We'll continue with examples. Okay, I want to do with you a problem on the analogy between electrical systems and thermal systems, because this involves how we can deduce variation of temperature in a certain domain function of the boundary conditions. Okay, and this will also involve convective and conductive fluxes. So let me introduce the problem. Sorry, 1 second. I'm just opening a whiteboard. Okay, the idea is the following. We have a cylindrical rod, let's say, and we have inner and outer. So this is used a lot in heat exchangers. Okay, if we have two fluids, one that is getting in, okay, and another that is moving out, and we want to determine what is the temperature distribution within the solid material. Okay, so we have two fluids, one characterized by T infinity 1 and a convective coefficient H1, and it's moving inside the annulus, and another one moving out characterized by T infinity 2 and convective coefficient H2. Okay, and they give you also the characteristic of the material. They give you the conductivity K, and they give you the of course the length of the rod and the inner and outer radius, R inner and R outer. And we want to determine in this problem what will be the surface temperature on inner side or outer side. Okay, so in such problems, how should we think? So first, who can tell me, if I give you this given, how can you start?
Transforming everything to thermal resistance.
Exactly. We want to transform everything to thermal resistance. If we want to build a circuit, okay, for this circuit, what do we have first? What is the first node?
T infinity.
Okay, it's T infinity 2. Okay. Now, what will be the first resistance?
For the convection H2.
Very good. So the first resistance is 1 over H2 times A2. And what is the second resistance?
Conduction.
Conduction. Very good. It's conduction through this cylindrical annulus. Do you know what is the formula of the resistance for an annulus? By the way, you don't have to memorize anything. We don't know it. This is why we'll derive it together. And in an exam, I can give you steps that will help you to derive it. So we don't know it. Let us say we don't know it, but we just say we want to find Q conduction for a cylindrical wall. And we'll see together that it's different than Q conduction, resistance of conduction, sorry, for a plane wall. It will be different. You remember what is the resistance of conduction for plane wall? If you go back to the course material, we derived that it's equal to L over Ka, okay?
Ka.
Yeah, however, for a cylindrical rod, it will be different and we'll find it together. We'll see how to find it. So I will call this temperature, if you want, T out, because, or T surface 2. And sorry, I will call the temperature here T surface 2, just in contact with fluid 2, while the temperature after considering this thickness, I will call it T surface 1 because it's in contact with fluid 1. Okay, and now what will be the third resistance? Again, we have convection now with the flow that is coming in. So it's T infinity 1. And again, T infinity 1. Again, it's here 1 over H1 times.
Professor,
Yes?
I have a question. The problems
Yes.
you're doing now are the same ones that are posted on Moodle or no?
No, they are not the same. Of course not. I'm doing for you extra practice. Okay.
Can you also post these on Moodle?
Yeah, of course I will. Of course. Yes, I will add a file. I will add a file with the problems you are doing in live sessions. Okay.
Okay, thank you.
Welcome. Okay. So now, the only challenge for us will be to determine what is this resistance by conduction. To know the procedure of how we find it, okay? First, in general, what is the resistance? We treat the resistance as delta T over Q, okay? Over Q. So this is why, for example, for convection, how we write Q, we know that for convection, so if you want to determine what is the resistance in convection, we say it's equal to delta T over Q convection, where Q convection is HA times delta T. Okay, then what will happen? Delta T will simplify. This is why R of convection is given by 1 over HA. For the case of plane wall, we said that the resistance of conduction. So let's say we have a plane wall. In a plane wall, we can show that the temperature distribution is linear. You know why? Because if I give you the energy equation, so how you know it will be linear? I will give you the equation. I can tell you that for steady state process through a wall, the equation driving temperature variation is that the second derivative of T with respect to X is a constant. I can just provide you this information. If I give you this information, you can proceed on your own. Because if the second derivative of variation of temperature in the wall is constant, this means that the first derivative of T with respect to X, here second derivative is 0. So I tell you, in a plane wall, temperature variation is governed by the following differential equation. Find the variation of temperature within the wall. So you say then that del T by del X should be constant. And then you can say that T is varying in a linear way. So you can write T as T equal to a certain slope A times X plus B. Okay, and to exactly know how the temperature is varying, you need to define two coefficients, A and B. And then you need boundary conditions. You need to know, or I give you the surface temperature. So I tell you T surface 1 is equal to this value and T surface 2 is equal to this value. Then you plug in to get A and B. Or also, second approach, I can give you, as I did in this problem, I can give you T infinity 1, T infinity 2, and the convective coefficient. And we'll remember now in this problem how to proceed to deduce the value of TS1 and TS2. But what I care for is, once I give you this profile, this equation, you should know how to continue. So if I give you this equation here, I tell you in a plane wall, the second derivative is 0. You tell me then del T by del X is a constant. And this means that delta T over delta X is equal to the rate of variation of temperature, because you know when the del T by del X is a constant and when you have linear variation, how you can get the slope? You can just do delta T over delta X. So if the thickness here is L, then you can say that del T by del X is just equal to delta T over L. And going back to the equation of the resistance, we know that the resistance of conduction is delta T over Q conduction. So now let us replace together. If we replace in this equation, we have that R conduction will be equal to delta T over, what was the expression of the conductive flux? It is K A times minus dt by dx. Minus dt by dx, okay? And minus dt by dx is delta T over L. So here we are just taking delta T as absolute value, the largest temperature minus the smallest one. So if I replace minus dt by dx by delta T over L, what will happen is that delta T will cancel out and I come up with my known formula of resistance, which is L over Ka. Okay, now we'll move through a similar approach, but now in case of a cylinder. So in case of a cylinder, I will tell you the following. For example, you have a cylinder. I will tell you that for a cylinder, the differential equation driving variation of temperature is del by del R of K R times del T by del R is 0. So this is the only information I provide you. How you can proceed? You say, if I know that this differential equation is driving variation of temperature in my cylindrical system or in my annulus system, okay? I can say that first I integrate. So let us integrate the first time with respect to R. What do we get? We get that KR times del T by del R is equal to a certain constant C1. Okay, now I will take KR to the other side of the equation in order to integrate again, because I need to do double integral if I want to get the temperature. And if I'm just caring about, if you want the flux Q or the heat rate Q, I don't need to get the temperature with time. So I can just say, what is del T by del R here? I can say that del T by del R is equal to the constant C1 over K times R. Okay. And now, what will be my conductive flux? You know that the conductive rate Q, okay, Q conduction is equal to, in this case, if the variable is R, we can express it as minus Ka del T by del R. And we replace del T by del R by its value. So we have minus K. Concerning the area of conduction is what? What is the area through which you have conduction here? If you have one-dimensional conduction in R direction, what will be the area through which you have the conductive flux? So you will have conduction in all directions. Who can tell me what is the area? Yes, it's pi dl or 2 pi r times l, exactly. Okay, so I will put times 2 pi r times l, and now I will replace del T by del R, okay, by C1 over KR. Now, as you see here, what will happen is that K will cancel out. If I'm considering, if you want C1 over K, K will cancel out, and R will also cancel out. So what I need to do is just to find what is C1, because I cannot proceed if I don't find the value of C1, okay? So to find C1, I need to continue my integral procedure, because C1 is a constant that I found from when I did integration. So to get C1, I need a boundary condition. This is why, in general, in such problem, I can find C1 and C2, which is the second constant of integration, from boundaries. So we know that we have two characteristic surface temperature, T surface 2 and T surface 1. Okay, so let us try to find C1 function of these temperatures. So what we'll do now, we'll say, if we integrate this equation again, we already found out that KR del T by del R is equal to C1. So del T by del R is C1 over KR. Let us integrate again, we get the following. So we have reached the following state. Del T by del R equals to C1 over KR. If we integrate again, we get the following. We get that the temperature T is equal to C1 over K times ln of R plus C2. Now, the constant C1, C2 will depend on the boundary conditions. So we have at the inner surface, we said that the temperature is TS1. And at the outer surface, the temperature is TS2. So if we apply boundary conditions, we can say the following. We can say at R1, at R equals to R1, T is equal to TS1. So let us replace in this equation. What do we get? We get that T1 is equal to C1 over K times ln of R1 plus C2. And now let us apply the condition at R2. So now if we apply at R2, at R equals to R2, the temperature is equal to T surface 2. So then we get that TS2, so this is TS1, TS2 is equal to C1 over K times ln R2 plus C2. Now, since I am interested only in C1, I don't care for C2, I can just subtract equations because this is equation 2, this is equation 1, okay? If I do equation 2 minus equation 1, I get the following. So 2 minus 1 will give me that TS2 minus TS1 is equal to C1 over K times ln R2 minus ln R1. But you know that ln B minus A, ln B minus ln A is ln B over A. So you can write just ln R2 over R1. So now we can deduce what is C1. We can deduce that C1, the constant C1, is equal to TS2 minus TS1 times K over ln R2 over R1. And now we are ready to calculate the resistance. Yes? Yes, I hear you. Can you ask your question, please? Do you hear me? I will continue. Look, in case you have a question and I'm not hearing you, please post it in the chat. Okay. So now, after we got C1, if we go back to the expression of our flux, we can get what is Q. Okay, let us write it together again. So Q, we said Q is Ka. So it's minus Ka times del T by del R. Okay. And we said that we replaced the area by 2 pi r L. And we replaced delta T by del R by C1 over KR. And now we found out what is C1. So let us replace C1. So we simplified this, K and K, R and R. Okay. Now let us replace C1. So we got that this is equal to minus 2 pi L. We have for C1 TS2 minus TS1 times K over ln R2 over R1. And now we can deduce the resistance and conduction, because we can say that the resistance and conduction in case of cylindrical wall can be calculated from delta T over Q. Okay. Now we said that when we consider delta T, we take the highest minus the lowest. So here it will be TS1 minus TS2 over. So here you can take the minus inside here. So you get over 2 pi times L times TS1 minus TS2 over ln R2 over R1. And now what will happen is that TS1 minus TS2 will cancel out. So these two terms will simplify. Okay. And then you can deduce what is the resistance. The resistance of conduction in cylindrical coordinates. If you just take this term to the numerator, the resistance will be R equals to ln R2 over R1 over 2 pi L. Okay. So you can see that the expression is quite different from the case of plane wall, because the differential equation in cylindrical coordinates will lead to a result that the conduction rate, okay, is given by delta T by delta R will not be just a constant. So you don't have a linear profile of variation for temperature. No, you have a logarithmic profile of temperature variation if the wall is cylindrical. And that's why you have a new expression for the resistance. Once I know what is the resistance form, now I am nearly done. Because all I have to do is to go back to my electrical circuit. I do it again. So this was my electrical circuit, let's say. Okay. Just we considered first that this was T infinity 2. This is T surface 2. This is T surface 1. And this is T infinity 1. Okay. And look, it depends which one is larger to know how the flux is moving. So if T infinity 2 is larger than T infinity 1, your flux will be in this way. If we are working in the opposite way, so if T infinity 1 is larger than T infinity 2, then you can know that your flux will be moving in this direction. And the rule to get, if you want your total, the value of your flux, is to say that your flux can be computed directly from T infinity 1 to T infinity 2. So let us say in this example, I give you T infinity 1 larger than T infinity 2. You just say that Q, which will move through your system, is equal to T infinity 1 minus T infinity 2 over the total resistance of your system. The total equivalent resistance. So sum of R, because you have here 3 resistances in series. So you do Q equals to T infinity 1 minus T infinity 2. Now let us sum the resistances. We said the first resistance is the the convective resistance. It's 1 over. So it's 1 over H1 times A1. And A1 is 2 pi R1 times the length L. Plus, we have now found together the expression of the conductive resistance for cylindrical wall. We have found out that it's given by 2 pi. So first ln of R2 over R1 divided by 2 pi times, okay. Sorry, we have here, I think, yes, still L. Okay. And we have also the resistance of convection. So 1 over H2 times 2 pi R2 times L. So now we have everything. We have everything in this equation. So all we have to do then is to replace and get the value of Q. And once we get the value of Q, then it becomes very simple to proceed. So when we get the value of Q, we say that we can calculate all temperatures. You know why? Because once you have Q, you can divide it. You can say Q is the flux between T infinity 2 and TS2, and is the convective flux. And at the same time, it's the conductive flux between TS2 and TS1. And also it's the convective flux between TS1 and T infinity 1. So once you find Q, to get TS2, you say Q can be calculated as H2 times area 2, which is 2 pi R2 times L, times delta T, where delta T that you will use here will be TS2 minus T infinity 2. So this equation can give you what is the value of TS2. Since once you calculate the Q, you are able to find now QS2. Then to find TS1, you relate TS2 and TS1. You say that through conduction process, I can write that Q conduction. So Q conduction, this flux is equal to the conductive flux, is equal to the conductive flux through this resistance. Okay, we said that we obtained its expression in cylindrical coordinates. So we replace back, okay, we replace back by T surface 1 minus T surface 2 over the resistant conductivity, the resistance of the conduction through cylindrical system, which is here. So we just plug its value here. And we have the value of TS2 from previous analysis. So we can get now TS1. And finally, to get, so here you can verify that your TS1 value is right by verifying that it's equal to H1 times the area 2 pi R1L, so times A1, times delta T, which is T infinity 1 minus TS1. So you can solve for all your temperatures by going through this procedure. Any question on this, on the thermal resistance concept and how we do the analogy between electrical circuits and thermal systems? Please, if anything is not clear, I can repeat. Okay, so this was some review problems on chapter 2. Next time, I will introduce for you chapter 3, and please try during this week to go over the remaining problems and try to do the assignment of chapter 2 to make sure that you grasp all concepts related to chapter 2. Before we stop, do you have any question on previous examples or on the research paper you are writing? Okay, so see you next time. And as usual, please, whenever you have any problem or question, you can directly contact me by WhatsApp. And also, we can organize office hours whenever you want, if not within the live sessions. And feel free to contact me if you need anything. Yeah, see you next time. Bye.
Thank you, doctor. Have a good day.
Welcome. Bye-bye.